This video primarily showcases the dynamic results of our experimental research, as presented in our paper, titled Flexible Active Safety Motion Control for Robotic Obstacle Avoidance, a CBF-Guided MPC approach. We divide the main content into 3 parts. We begin with Test 1, Comparisons between FASM control and MPC. In this scenario, we test the proposed method involving the fast-moving small obstacle with the prediction horizon n equals 1. The proposed method successfully avoids the dynamic small obstacle. The joint velocities satisfy the constraints. The position and posture errors eventually converge to 0. In this scenario, we test the proposed method with the large obstacle, with n equals 1. The proposed fast control successfully avoids the dynamic large obstacle, even with n equals 1. The joint velocities satisfy the constraints. The position and posture errors eventually converge to 0. In scenarios C and D, we test the classic MPC method involving the fast-moving small and large obstacles, with n equals 1. MPC fails to achieve dynamic avoidance of both small and large obstacles with n equals 1. The safety criteria in MPC become active only when the robot is in close proximity to the obstacle. In scenarios with fast-moving obstacles, there might not be adequate time for the robot manipulator to avoid obstacles. Test 2, Comparisons across different p-gamma. In this test, we investigate the impact of different values of p-gamma on the performance of the proposed method. We specifically concentrating on the scenario of slow-moving small obstacle under p-gamma equals 150, p-gamma equals 1000, and p-gamma equals 2000. During the obstacle avoidance process, gamma k is dynamically optimized, thereby providing flexible safety constraints. Different values of p-gamma provide adjustable safety margins, with larger values corresponding to greater safety margins. Specifically, p-gamma equals 150, 1000, and 2000 correspond to small, medium, and large safety margins, respectively. As shown by the table, larger p-gamma results in a higher lift of the end effector. Larger p-gamma results in more advanced avoidance actions. Larger p-gamma leads to smaller overall values of gamma k. In general, p-gamma offers adjustable safety margins, where larger p-gamma leads to smaller overall values of gamma k, which correspond to greater safety margins. The flexible CBFSC employs dynamically optimized decay rates to prioritize active safety when the robot is distant from obstacles. It then gradually relaxes safety constraints as the robot manipulator approaches obstacles to improve the feasibility of optimization problems. Test 3. Comparisons with MPC CBF methods using fixed gamma k. In this section, we compare the performance of the FASM control with MPC CBF methods using fixed decay rates. As illustrated by the videos, the proposed FASM control effectively avoids the fast-moving large obstacle across different values of p-gamma, each corresponding to distinct safety margins. As shown in the videos, the MPC CBF methods effectively avoid the fast-moving large obstacle when gamma equals 0.01 to 0.2. but fail to avoid the obstacle when gamma equals 0.3. For details, we show the performance of the MPC CBF methods with gamma equals 0.25 and gamma equals 0.3. The collision occurs because these fixed gamma values are too large, leading to overly loose safety constraints, and a failure to initiate timely avoidance maneuvers, as illustrated by the table. we show the performance of the MPC CBF methods with gamma equals 0.01 and 0.05. The small values of gamma enforce stricter safety constraints, allowing the obstacle avoidance maneuver to be initiated earlier. However, the overly conservative choices of gamma result in a large RMSE, reflecting low efficiency in the obstacle avoidance trajectory. The performance of the MPC CBF methods with gamma equals 0.1, 0.15 and 0.2 outperforms that with gamma equals 0.01 and 0.05, achieving successful obstacle avoidance and lower RMSE. However, as shown in the table, our proposed FASM control method with P-gamma equals 200 outperforms the MPC CBF methods, including higher obstacle avoidance heights, faster response times, and the smallest RMSE. This is because our method dynamically optimizes gamma K within the range of 0 to 0.2416, providing greater flexibility than a fixed gamma. Overall, our method dynamically adjusts safety constraints in real time by optimizing gamma K at each time step. Initially, a small gamma K is used to trigger early avoidance, and it is progressively increased during the avoidance process to improve trajectory efficiency, ensuring a balance between safety and efficiency in obstacle avoidance. The proposed FASM control method significantly outperforms constant MPC CBF gain methods. By dynamically adjusting gamma K within a range, our approach effectively optimizes the trade-off between safety and efficiency. In contrast, constant MPC CBF gain methods lack flexibility, often leading to overly conservative or inefficient performance.